Okay, so folks, we're gonna get started. I'd like to welcome again, and again, it's a real honor to be here with you to share with you this week related to conceptual underpinnings, education, and some training related to agent-based modeling here in AnyLogic. I normally like to begin my my days with a retrospective on what we saw yesterday. Just to sort of reflect on the context. So yesterday was a shorter session, and after a round of introductions, we began with a bit of orientation material where I noted some of the resources afforded to you. And I wanted to specifically note an update for one of those resources that has occurred since the last time, and specifically the YouTube videos for the site. The first of them are now uploaded. There's 6 videos on the YouTube playlist. I provided you the link as part of your orientation packet available up here, and you'll find the videos on there. We've adjusted the audio a little bit today. It sounded like it was maxing it out a little bit of times yesterday, but if there's any other quality issues you note with the videos, please do let me know. Those of you who weren't here yesterday will find those videos of particular relevance, but we will be undertaking examples today which don't directly depend on those exercises we undertook yesterday. Don't directly depend mean you don't have to load in the model you built yesterday or a similar pre-existing model. We'll be sort of going through many of the steps we went through yesterday again today to build your basic strength training in AnyLogic. So that's one issue. So you'll find those videos expanded and enriched online. I would again refer you to that reference card, the AnyLogic reference card, for providing guidance on several of the little snippets of code we used in the course of the day yesterday. Several of the snippets we used to accomplish certain things. Things like making the color of that circle dependent on an agent's sex, or making it depend on someone's income, the location depend on an income, etc. We then went into a bit of discussion concerning basic AnyLogic interface by focusing on an example where we were running the model with a canned sort of model loaded that came with AnyLogic, and we saw our first glimpses of the basic concepts of AnyLogic associated with agents, a population of agents, each of whom had some properties, some state that evolves over time, and some dynamics describing the evolution of the state. And we saw that in AnyLogic how much of that evolution is characterized declaratively. We specify more the what of what we want to accomplish and less of the how, and it takes care of a lot of details. Examples would be exactly when someone recovers. We just say we want this to be exponentially distributed. It proceeds according to some rate, some lambda, and it will take care of deciding exactly at what time they transition from one state to another. We saw that AnyLogic's time is by default continuous, meaning that you're not going and doing things in a step-by-step, lockstep manner, sort of batch by batch. Instead, things happen over time in a continuous fashion. It will handle things that happen really, really quickly where necessary. Maybe a situation where there's a lot going on, say an early part of an outbreak, and then some periods, which are periods of stasis, it may jump from event to event with much longer periods of time between events. It'll handle all of that. One of the nice features of that I didn't emphasize is that if you have competing risks of sorts, competing events, say between getting infected and death, rather than having to broker them on a time-step by time-step process, which occurs first, etc., they just happen at their natural times. And if someone dies before they're infected, they die in an uninfected state. If they get infected prior to death, they're recorded as an incident case. So that's a kind of nice feature of not going these quantized steps, these ticks that you'll see in some other platforms. AnyLogic does support that if you want recourse to it, but by default, it's continuous. We also saw that we could define these experiments for models, and these experiments were delineated with a visual representation that had an X next to it, and they basically depict scenarios for the model, scenarios which have associated with them certain assumptions. So if we click on that experiment here and we go down to this properties window, which shows us the properties of whatever is selected over here in the projects or over here in the canvas, we can see when we scroll down that we can specify the parameters associated with this. And in fact, we didn't have any, I should have used a better example. We didn't have any parameters associated with this particular model we built up yesterday. But if we look at the model which we actually used in that first session, what we'll see is that there's a set of parameters associated with main. So, oops, here's main here, and we have a set of parameters associated with it, which are just over on the left-hand side here, hidden. And if we go look at a particular experiment, we see it specifies assumptions to put in place for those particular parameters. And different experiments will differ in their assumptions. For example, a long duration of infection will have an average illness duration here of 50, shorter of 10. Okay? So these are scenarios where we're running the model with different basic assumptions captured that differ in degree of some sort. Typically, it's in degree. We'll see later a more advanced use of parameters. We also saw how fundamental a difference could be obtained by modifying the structure of the model by, say, adding a transition in here where there was none originally, so that people have waning immunity. If they exhibit waning immunity, so after some period of time they lose their immunity, we saw that that could very materially impact the dynamic seen with the model. We also noted the occurrence of stochastics. So running this model, for example, in its default set of parameter values, its so-called baseline case, we saw that, particularly it's pronounced early on, but as time goes on, been around it, while there's some general regularities, some structure to the results, there's also vagaries of chance as to exactly when people are infected, hence this kind of ragged periphery associated with this expanding wavefront. We saw that this was an emergent property of the model. In no way was it presupposed or programmed into the model. In no way was it hard-coded, hardwired in. In no way was it fixed into the model that we would have these expanding patterns, these waves of infection. Rather, it was a property that came about through the nonlinear interaction of diverse components of this model, including the natural history of infection, including the fact that agents, as in many models, are situated in some context, here a spatial context, so that people are associated with their neighbors and can infect their neighbors. We saw where that was encoded in main here, that people were arranged in a certain neighborhood, one of two types, and they were placed in space in a regular grid. And then by sending these messages, by sort of letting people know that they were exposed to a bug or to an idea or meme, we could send to neighbors in space, and that would infect those people. So this little model exposed us to many features of AnyLogic as a platform, including the window management. And I noted some basic ways in which you can run the model. You can speed it up and slow it down while it's running using these buttons here, this one running it as fast as possible. If you want to inspect what's going on, you can go into modes where you can make it slower or make it faster, but have better control over the time. You could stop it and pause it. Okay? These are all basic skills. And we noted that the basics of this interface could be sculpted by these menus here. Okay, so that was our first little exposure. I then went into a bit of a discussion as to the basics of agent-based modeling, noted the essential features of an agent-based model. So we have one or more populations of agents. Each of those agents is described with respect to their state, their basic properties that are not changing that quickly as well. There are things characterized in any logic by parameters, but features like their sex, their ethnicity that are discrete, but also features that are continuous, things like their birth weight, things like their height. These are continuous features and are notable because they're hard to capture in an aggregate model in a fine-grained way. Moreover, those agents are associated with some rules for their evolution. Those rules are predominantly described declaratively in many agent-based models in any logic. So here, a state chart characterizes the rules for evolution of this agent, and in general, we may have many such mechanisms. Stocks and flows are another declarative mechanism you can use for agent evolution in any logic. And those agents are situated in an environment where they can interact with other agents. Typically, we see stochastics in this context, and we can create multi-level models as well for characterizing the evolution. We noted that in contrast with the system dynamics model, an aggregate model where the model is organized, divided up according to state of people in the population, the count of people of a certain state and characteristics are counted up for each category. Here we're organizing the model according to persons, and each person's state and characteristics are maintained by that person, okay? And I noticed some strengths of agent-based models I won't go into in detail here at all, but they include the capacity to carry longitudinal data on individuals rather than having a cross-sectional depiction of a population over time, ability to capture things like network context, spatial context, the ability to capture multi-level structures, so multi-scale modeling, and the ability to represent aspects of individual choice, agency, decision-making that's based on preferences and perception of a situated context, what that particular agent can see. Think about a model of cars driving and what you're on a windy road, and what you're capturing is what that particular car driver can see from their position. That might cause them to speed up or slow down based on their situated perception of the situation. So if you want to capture that and capture preferences and its impact on decision-making of agents, agent-based modeling is a particularly attractive approach. Ability to capture heterogeneity was another virtue that recommended it. I discussed a little bit of motivations for this sort of modeling, the ability to tease apart and help set priorities for intervention and for data collection in problems that are causally tangled, where we have all these interacting factors that shape the success of an intervention or shape the evolution of the health of the population over time. We then went into our main focus for the afternoon as far as a practical exercise where we built up this model that stands before you now. So we built up a model where we had, as a learning model, no representation of evolving agent state, but we introduced heterogeneity in agents. So we saw that in any logic, we have this main class, which describes sort of the stage in which the agents strut, the stage in which they circulate and interact with each other. And we define then a so-called class. This delineates, that's called person. It delineates personhood or personness with respect to how we want to capture it for this model. All models, like all maps, are abstractions. They allow us to do useful things because they simplify the situation and allow us to reason through it. And like maps, models are specific to purpose. When you need to drive across Raleigh, use a street map. If you're interested in why flooding occurs in certain areas of Raleigh, you'd use a hydrological or topographical map that shows where water collects. And so it is with models. A given model will capture certain features of a situation and hide details of other features. And therefore, it stands to reason that our models, when we depict personness with respect to a given model, it'll capture different features of the situation. So person here depicts personness, and when we run a model, or personhood, what's our sort of theory of personhood that we want to explore the implications of in this model? And when we run the model, we'll see many particular persons, each with different characteristics that reflect the fact that personhood associates people with age, sex, and income, and now we have a population where we have people of different ages, sex, and incomes. Particular values associated with those parameters. So these classes capture our notions of, in this case, an agent class, personhood or personness as a whole, and then we have particular instances of it, as we call them, where you have particular instantiations of these attributes to be particular values. Okay. Now we did note that these attributes could be associated with general characteristics. So age, for example, is a double precision value, as is income. But sex here was a value that was called sex, and it was defined by the capital SEX characteristic, which delineated sort of the set of possible sexes, the general concept of sex, so male and female. And this was an option list we added to AnyLogic for the purposes of our particular model. So we did new option list and described this option list where we delineated these characteristics which could apply with respect to the categorization of sex. We further noted that we could make the appearance of people within the model dependent on the characteristics of a person. So, for example, we could declaratively say we want the fill color for someone to be defined by their sex. If their sex is male, be gray, otherwise be yellow. We could, moreover, have other aspects such as their radius be set by something like their age. And that was useful to illustrate sort of the characteristics of the model. Once again, we're specifying more of the how, the what here, what we want to be the case, and AnyLogic will take care of making it happen. Even if age and sex were changing, it would take care of making sure they stay consistent. We further explored this by setting people's location to be dependent on their income. So here we saw we could tell AnyLogic, hey, just put them in a randomly scattered way if desired. We did that in main by scrolling down and indicating originally a layout type that was random. But then later we refined it by saying, well, no, we actually want to take care of it. We want to impose instead a user-defined network or user-defined layout, and we'll take care of putting them in the right place. So we went to population and we indicated where people should be placed by their X and Y location. The Y location was drawn from a uniform distribution between 0 and 500 for where they were located vertically, and the X location was set by a formula here. And that led to a situation where people's X location was reflective of their income. Okay, so we had them stretched out along here. So that was a useful thing. We also found that we could do something like click on people, and we could tell it when you click on one of these people, print out some information on them. And it had printed out in a place called the console, and I'm going to view it here by view console. It's a somewhat fickle window unless you pin it. In here, we could have it so when we clicked on someone, it would print out their attributes. How did we do that? Well, we went to person. In general, if we want to set a characteristic of someone, sort of how they behave, for example, what sort of information they maintain, if we want to set it for a person, we go to the person class. It denotes personhood. And we saw we could click on this oval here, and then we could go in the oval, and we could specify a so-called click handler, an on-click event, so that when you click them, it prints out this information. And this trace ln just says, hey, print this out to the console, okay? So it printed this thing out. And this basically just printed out these strings with some appropriate information substituted in successively. So that was useful. And a final little element I'll emphasize we saw that the characteristics of a person are basically delineated by the person class, but the particulars, so in other words, the fact that they have an age, sex, and income, those aspects of personness are delineated by the person class. The particular values to assume for those are delineated by the population. And so if we go to population up here, we can go look how do we determine for the people in the population, what particular values should we assume for their age? Well, we should draw that from a uniform distribution. What particular values for their sex? Draw that from choosing with uniform likelihood from their sex, possible values of their sexes, of their sex. For their income, notably, we imposed a conditional distribution. So their income was determined based on whether they were male or female to reflect the gender disparities we see. Here, if they were male, they had one distribution. If they were female, they had another distribution for income. Notably, although I didn't emphasize this yesterday, it bears noting here that I was able to do that because I defined sex before income. So if you're going to have dependencies in this sense, try to add the parameter for the parameters on which you're going to depend, your sex, before you add the ones that depend on them. Okay, little bit of a nuisance there. If you find yourself in a situation where, oh, you forgot to do that, you can always delete them and add them back in the right order, and it'll be fine. Okay, so we did a lot in that example. There's a lot going on there. Any questions related to that example before we go on to new territory? No questions? Okay. So one thing that I wanted to note, based on feedback from the exercise yesterday, be very careful when you're adding things into the model as to where you're adding them. Are you adding them into main, or are you adding them into person? And I would suggest reflexively looking up and see, okay, the canvas that's being described here, this place that describes sort of the current object, what is it? Is it person or is it main? Before you drag things in. Because it's very easy for me as well when I'm tired to sort of drag it into the wrong thing. And it's important. Certain things live in person. The appearance of a person lives there. Their characteristics live there. The state charts that describe their evolution lives there. Other things live in main, things like the population, things like parameters for the whole model, etc. And it bears some thought about to where you drag them in. So try to reflexively look up, is it in person and main? And if you have an error, double check that you haven't added it to the wrong thing. It occurs commonly, okay? So that is something you might want to bear in mind when you're trying to avoid mistakes or smooth mistakes that you have made. Okay. Any other questions then? Yes.
So I was wondering, is there any fish as to know when to use item, when to use cell?
Good. Yes, there are. There's for the most part, there's a context that will give us that information. So if you go to main, for example, and right, because you're referring, good point, we added statistics to this model. I didn't emphasize that. So you'll notice that with this population, we sometimes use self, we sometimes used here, for example, self and above, and we sometimes used item. For the most part, and it's not without exception, I'll point one out, for the most part, this is indicated using these little light bulbs here to the left-hand side. So for an example, it says index, replicated person, then self. It's telling you self is available for your use. So that's one way you can know. And similarly down here, when we define the statistics, which declaratively specify what information should be available for computation, there's a little button here that says item is the embedded object. And it's not very transparent as a description, but what it's telling you is, hey, item is available for use, and it reminds me, oh, I can refer to so the statistic is applied to each and every person in the population in turn. And it checks, okay, is the condition true? If so, I'll take, in this case, the average of this expression here, their income. Each successive person in the population is in turn given the name item and evaluated for inclusion in the average, right? And item here is referring to the name for each successive person. So for each person, it will take their income and take its average. So that item is given as a name by this little light bulb here. With statistics, notably, when you run the model here, those statistics normally won't be computed unless you request them. But if you do click visually on this model, it will, on the population, it will actually print out the statistics you've defined for that population there. But there is one important, there are cases where that information, those hints, are not present. And specifically, if you go up to population, and Priyasri, you could take this down as something we should ask them to fix in AnyLogic. You'll notice that in income here, it doesn't tell you about self. That's something which is not part of the hints. And so when you're doing these parameters for a population, they don't tell you that you can refer to the person as self, okay? Now, there is another way. For those who are not faint of heart, well, those who are bold, if you want to know something about the context, you can go in here and you can actually put your mouse in that formula and you can press Control-J and see actually what is being done in the underlying code. And here you'll see it's fairly transparent. We're setting the age of this thing called self to be uniform 065. We're setting the sex of that to be random from this, which is from here. And then we're computing their income based on these characteristics. So you can actually see the code that's produced, and you'll notice that self is defined up here. Is that helpful? Okay, very good. I don't like to look at this code, and generally you don't have to look at it very much, but sometimes you may seek recourse to that to know exactly what's going on. Okay? Okay. Any questions? Yes.
So mine is silly. My windows look different than yours.
Okay. Yep. Great.
And I can't seem to figure out how to get them one on top of each other instead of one beside each other.
Okay. Priyas, maybe you want to help. Maybe I could show you a little bit about window management, and this may help. And Priyasri, why don't you just watch while I'm doing this in case it's something Kristen wants to try herself. So in general, AnyLogic's interface. So maybe what I'll do is, with your leave,